I'm Tautvydas. I work in Unity Windows Phone development team. We'll be speaking about mobile performance.
Hi, I'm Zbigniew. I am QA guy who is mostly responsible for mobiles and graphics. So, we'll try to help you answering this crazy question probably everyone has in some point of releasing a game. We'll just give you some basic tips how to solve it, what not to do or do. And in the first part, it will be general performance stuff. In the second part, we'll talk more about tools and how to profile and get down to what is actually bounding you and limiting. And it's mostly focused for probably newer users. So if anything is too easy, just calm down, you are great and you know everything.
So let's first define what's performance. It always comes down to the perceived smoothness of your game. Probably the biggest factor in that is the frames per second. Usually the games that are below 30 frames per second feel very choppy. Below 20 is generally unplayable. And ideally you'd want to aim for 60. That's the refresh rate of most mobile devices screens. Realistically though, reaching 60 frames per second is pretty hard. So you can just aim for 40, 50, and it feels much better than 30. There's one more thing that is perceived smoothness, that is responsiveness. It is closely tied to frames per second. However, it's also tied to how you process your input. So don't delay, do it as soon as you get the events. Yeah, the main causes of bad performance. There's one more. There's only one cause that's doing too much stuff. It's either on CPU or on GPU. Either you have too many objects in the scene, they're either too pretty, or you have just have too many scripts doing unnecessary stuff. Well, if your game looks like this, you have a problem. GPUs have their parameters, and one of the main GPU parameters is called fill rate. That means how many pixels per second you can draw. The second one is triangle throughput. That is how many triangles you can pump out through per second. However, these are theoretical numbers. GPU manufacturers get them in perfect conditions. You'll probably not be able to reach them. They're only for ads, I guess.
So one of the high-end devices which is available and a lot of people use it is iPhone 5s. It has really great hardware and pretty low resolution compared to other like Android devices. So it's pretty fast. Its fill rate is over 3,000 million texts per second, and triangle output is 68 million triangles per second. And why do we care about that? Based on those stats, which you can find for every mobile in their tech specs, you check its screen resolution, and you can just calculate yourself how many times you can fill whole screen. So in this case, you just divide fill rate by resolution multiplied by your frame rate. If you just need a lower frame rate, like 30, it will be double that. So iPhone can fill screen 75 times every second. That's super great. Same for triangles. We have over 1 million triangles every frame, which is like probably a few years ago that was for PCs. But the problem is that we often have to think about lower-end devices like iPhone 4. Probably most of you need to think about it, and it has way worse hardware than iPhone 5s, and it uses almost the same resolution. So it's really hard to make your game work well on it. As you see, stats here are way lower, and you have 7 times lower fill rate. So you can fill screen only 10 times. This means that you have to be really careful with transparent objects, which cause that. And you have only 200 key triangles per second, which is like most of the games you'll be using for mobiles 10, 15K triangle objects. So you have to really be careful and think it through how many objects you want on your screen. Not because if you want to make an RTS game with 200 objects, probably it's not going to run on iPhone 4.
What we did was to measure the performance of various devices, and we tried to find the performance limits. It's really important to measure on the devices you want to target, because if you don't, your game will run like crap. Our testing methodology was to load the devices with more than they can handle, and then normalize that number to how much you can afford to without dropping below 60 frames per second. Our first benchmark was how many low polygon models with animation you can handle at the same time on the screen. This particular benchmark is bound by CPU. That means by draw call count. This is the number of various popular devices. On high end, you can see you can almost reach 300 of such little objects. On low end, you can, on iPhone 4, that's barely over 50. So keep that in mind. Next one was skinning performance on higher polygon models. This one isn't bound by draw call count, but it's instead bound by skinning. On mobile devices, the skinning is usually done on the CPU. So it's bound by matrix multiplication that comes from skinning. You can, with such high polygon models, you can afford much less of them on the screen at the same time. So keep your skin data low. The amount of vertices that you need to animate, really keep that in mind. Sprites. They are popular as well. In 2D games, they are basically the only thing you'll ever draw, probably. We tested tightly packed sprites. On slow CPUs, they're bounded by draw call count. However, on most mobile devices today, they're bound by GPU fill rate. With sprites, you can generally afford way more than that. You can afford more than the normal models, 3D models. They're easier to draw. One thing to note, though, when using sprites, is there is a choice to choose which kind of sprite packing you want to use. You can either choose square packed sprites, and then the hit will be on the GPU. Since sprites are mostly transparent, and when you use the square packing, there's loads of transparent pixels there. When you use tight packing, Unity generates a mesh around the sprite, and that reduces the amount of transparent pixels you have to render. That takes a hit on CPU, but it saves you GPU time. Static geometry. It is essential to draw stuff with many triangles, and this benchmark demonstrates how many triangles you can draw when the objects take very little screen space. Generally, it's not a problem on modern devices, as it's realistically, you'll never reach that number. Even on lowest end devices, you can afford a few 100,000 of those triangles in the scene. Another very, very important point is transparent planes. This is the transparent objects you all know and love. You draw them, you use them for trees, you use them for many objects. However, transparent objects are really, really heavy on the GPUs. They're mostly blending stage bound. That means when, after the pixel shader, it has to merge the pixel with the one that is behind him. And that operation is very, very expensive on today's mobile devices. You can't afford many of those planes at all, filling whole screen. So you have to be careful where you use them. Next one is opaque planes. This one tests the device fill rate. We're drawing many parallel planes that are composed of 2 triangles each. If you're rendering on low resolution, you're generally fine. But when the resolution increases, you get fill rate bound, and it really goes down. One important thing to note here is if you look at the devices, for example, there's Nokia Lumia 520. That's the cheapest Windows phone you can buy. However, it's faster than the 1520. The only reason for that is that 1520 rendering resolution is 5 times higher. I suggest you, if you're getting fill rate bound, you can just reduce resolution, and that will really help you. So what did we learn from these benchmarks? Bigger objects are better than loads of small ones. It doesn't change the load on the GPU. However, it reduces the load on the CPU. That means you can afford more draw calls. Also, you need to use the opaque shaders where possible. Transparency kills performance really, really fast. And of course, keep the dynamic geometry low. Only use that where it's really needed.
So another point is scripts, of course. We have them in every game. We use them constantly. So as with other aspects of bottlenecks, you should always avoid unnecessary stuff. That sounds easy, but how do we do that? Be especially conservative on amount of stuff you do on update. After all, it's running every frame. So if something is not needed, just move it to any other function which isn't constantly called. And even if you follow all the best practices you checked on, there are always situations where your game is laggy as shit and you have no idea why. So the best advice we can give you in those situations is just to start profiling and get down and to what is the problem and what's causing. So that's why we'll be talking about tools which are available in Unity, and just for every platform, some examples. What can you use and what should you use it for? You should try them all. Even if something looks maybe not optimal, it might give you some information which other tools don't have. Because a lot of different tools are best for only one thing. We'll show the examples. And when you know all the best uses, it will be way easier to find out what's wrong, and it will hopefully save you a lot of time. So first of all, of course, Unity Profiler. It gives in-depth look into different engine subsystems like CPU, memory, rendering, physics, audio. You can check out a huge amount of stuff in there, what exact functions are taking a lot of time, how many audio objects do you have in scene, and a lot of other stuffs. If you haven't tried it already, please do. You should spend a lot of time in using this tool because it's what makes your game really fast. It helps you find memory leaks. And so it's the best tool to profile what exact scripts are taking too long, it's probably the best tool to find what is causing that annoying spike when you, for example, collect a coin. And the problem is it's available in Pro, so free users can do that. Also, you can't profile GPU, for example, on iOS. That's a problem. So you have no idea what exactly is taking on so long on GPU side. That's why we have internal profiler, which is available on iOS and Android. How many of you have already used it? Please raise your hands. Okay, that's really great. Actually, I wasn't hoping that so many people know about it and use it, because if you don't have access to Pro, it's the thing to use. It's really easy. You just enable checkbox in player settings for Android. On iOS right now, you need to go into Xcode project, expand classes. You'll have a header named iPhone Profiler, and you need to change the value from 0 to 1. That's really hard, but I think you'll manage. So it gets output printed twice constantly. You get summaries of each 30 frames, and it really helps to quickly understand what's taking the most time. So you have an example of that sample. So we'll go quickly through all of the stuff and explain a bit about it. So first of all, it's CPU player. So it just shows you how long Unity takes executing our own code and your scripts. CPU OGLES driver, it's executing OpenGLS driver. It's affected by a number of things like draw calls, internal rendering states, rendering pipeline setup, and number of vertices, for example. CPU waits GPU, that's kind of obvious, I think. So it shows how long CPU is waiting for GPU. If you have a number here over 2 seconds, you are definitely sure that you are GPU bound, and you don't need to look at CPU for now. Just try to make your stuff less pretty, probably. CPU present shows you just one present render buffer function. How long does it take in OpenGLS? You probably don't really need that. Frame time. So probably the most important statistic you're always interested in is your frame time. So it just shows you how long that frame took. In this case, you see there is a minimum 32 seconds and maximum is 37. It's so because of evil garbage collection. That's the last one, mono memory. We see that there was only one collection and it took 5.7 seconds. So that's why that minimum and maximum are just differentiated by 5.7 seconds. Also, I guess in this sample, frame rate was targeted to 30 FPS. That's why it's not more, because other stuff isn't taking that much time. Also, it shows you stuff like draw calls, triangles, and vertices. You should mainly use that to check how well is stuff batched. You should be using dynamic and static batching, especially if you have problems with GPU. And so you just should try to share as many textures and materials for them, and you'll see the results if it's working correctly. And player detail shows you all of the subsystems, and you can easily understand what's causing that. So physics is physics, animation, oh, I don't know that, probably animation. Culling is culling, skinning is for animating skinned meshes, batching is for batching, and rendering, as always, is taking the most time. So in this case, you already know that your physics or animation isn't taking too much time. You don't need to worry about that. Just focus on rendering and optimizing that. And it also shows you the minimum and maximum amount the fixed update was called. Be careful with that, because if fixed update is called too many times, it can bork up your performance. And monoscripts, yeah, nothing fancy there. So on iOS, if you're using Xcode 5, which you should be, we still have users who use like 3.5, so you never know. So in Xcode, there is a Debug Navigator, which works only, unfortunately, with iOS 7 and higher. But like with all Apple products, most of your devices probably have iOS 7. So it allows you to check the most important question you should be always asking yourself. Are you bound by CPU or GPU? And Xcode instruments are really great, but mostly only to profile general script performance and real memory usage. That's the best way to actually know how much memory is your app using. You'll often see that iOS tends to kill devices, devices, right. Applications way before when you think it should. It's because Apple is really careful and doesn't want you doing anything bad. So be really careful with memory, and that's the best way to profile that. You can just press on Product and Profile. It will open the Instruments window, and you need to select Activity Monitor. So the Debug Navigator, which I told before, it has a nice icon, which I unfortunately didn't put in here. Like on the left side of the Xcode window, you have, I think, 5 symbols. It's probably 4th or 5th one. When you press on that, you can choose frame rate. It will also show you frame rate and what we are more interested in, CPU and GPU usage. That's the prime way how you'll figure that out. So in this case, it was one of the examples we had. It just renders a lot of stuff. Probably no scripts at all. That's why we are GPU bound. And it also shows you utilization of tiler and renderer and of the device itself. So as you see, it's using 100% of GPU usage. You probably can't squeeze out anything more.
Right, Android. Every Android GPU vendor has their own tools. There's loads of them. For Qualcomm, you have the Adreno profiler. NVIDIA has the Tegra one, and all the others are listed here. You can use systrace for any vendor, but it only allows you to profile the CPU. Generally, you would pick the problematic device, hook up the tool for your kind of device, and check what's wrong. For Windows, we have the Visual Studio Profiler. It allows you to profile CPU and memory usage. Visual Studio Profiler requires to have VS Pro. It's not available in the free editions. My favorite use of it is to capture memory snapshots. It allows you to capture the managed heap, and it will tell you exactly which object you allocated and and the stack trace that allocated them. That will tell you exactly what's causing the GC pressure and how to reduce it. Here's how it looks on our benchmark, the first benchmark. There's just loads of little objects on the screen, and we had 3,400 objects allocated that took almost 200 kilobytes. Right, event tracing for Windows. How many people here have heard about it before? A fair amount. I didn't expect that. Okay. This is the kernel-level system-wide mechanism to log events. How it works is that you enable the performance in the Windows Performance Recorder. You start the trace, And until you stop it, it tracks all the system activity, all the applications, everything, and writes it to a log file. Once you stop it, it produces an ETL file, which you can open with many different tools. That is Windows Performance Analyzer, PerfView, GPU View. There are way more than that. It's my favorite tool at finding performance issues on Windows because it really lets you go to the lowest level of your application. I'm gonna demo how it works because the documentation for it isn't the best and it's pretty not user-friendly. So this is an ARM tablet, has a Snapdragon CPU. What we'll do is enable the Windows Performance Recorder, and we'll record the events we started. It starts recording, then we go and start a game. We play for a bit.
Who hasn't played that?
It's a good game.
Was.
Yeah, that should be enough. You'd probably want to play the problematic part of your game. And once you're done playing it, you stop it, you save it. It takes a while. What it does is it takes all the system information. It takes all the assemblies in the global assembly cache. It extracts the symbols out of them. When you install .NET Framework on a machine, it kind of engens it, compiles it to native code, so it works faster. But because of that, each machine has a different debugging symbols, so it has to extract them so you could see exactly what's taking long. Once that's done, you have to transfer the file to x86 machine, normal Windows, and from there you can analyze it. Oops. There we go. It kind of produces these ETL files, and it also has the native compiled PDBs for .NET Framework. You need to copy that to x86 machine and then analyze it from there. Yeah, while it's copying, I'll hook up the other monitor. Okay. It's all copying, almost done. About 20 seconds remaining. Once that's done, you get to you can open the file, and by default it opens it with the Windows Performance Analyzer. This tool can display many stuff like storage, the I/O of. Whoa, you can't really probably see that. Give me a sec. Yeah, the computation, that's the CPU load. Storage, that's the disk load. The spike here is when I hit stop and it had to flash everything to the disk. and it can track memory usage. It tracks the events for the whole system. It doesn't track it for a single process. However, since we're only interested in our game, we just filter it to that. All right, you also have to tell it where to store the symbols. Where are the symbols for your compiled game? So I have the symbols right here. There we go. And you need to tell it to load the symbols, so you could see the stack traces. As you can see, this CPU profiler works by sampling stuff, by sampling your application, the stack traces in each sample. In the 45 seconds we had, it took 50,000 samples. You get to see each thread separately. Let's work out from the bottom. This one took about 10% of the time. Oh, wrong. We needed the stack, not a stack tag. Right, so let's see what we have. This is the Unity player. Oh, it's not loading symbols. Yeah, it's not loading symbols for some reason. I have a backup plan though. I have another trace which should work. Probably did something wrong. Maybe it wasn't the same binary, so the symbols didn't really match. That's a trace of Angry Bots as well that was captured a few days ago. Kind of interested in stack and thread ID. There are a bunch of more stuff you can see there, like function names. And if you need to go that deep, you can. There we go. Yeah, this is the audio thread, fmod. It's our audio system. It took a fair amount of time, but it's on a separate thread, so it's not an issue. What else do we have? This is the Windows event pumping thread. You can't really do much about it either. Audio. The top two threads are. This is the rendering thread. You can see exactly what is taking the most time. The most expensive call is draw D3D11 VBO. That's vertex buffer object, just basically drawing. Last one is the main Unity thread. That's where you'll mostly be focused. You can see all the Unity internals through here, but that's a good thing because it's not hiding anything from you. In Unity Profiler, you can only see stuff that we're exposing, and this shows you pretty much anything. So the most time is taken by rendering, a little bit less by GUI. GUI is really expensive, it seems, at least on Angry Bots. Next one is fixed behavior update. Let's see what's that. A bunch of stuff. Calls into CLR. And it ends up at assembly Unity script code. So you can see exactly which script is taking how much time and how expensive it is. In this case, the mech animation is the most expensive. And you can even see which exact calls into the Unity APIs are expensive. Let's expand that. The most expensive one is object get name. Who would have thought about that? Yeah, don't use strings, they're expensive. So with this, you can basically check the CPU performance and the stack traces. However, there are more tools for that. Another tool I'll show is PuffView. It can also open, give me a sec, I'll disable the magnifier for now. Probably need it later though. Yeah, this looks like a really old application, though I like it. It shows you the real internals of. For example, you can see how much did it take to JIT your methods on the device. You can't really do much about it, but it's interesting. It took 50 milliseconds to JIT all the methods. And you can even see each method separately. Mac attack move controller on enable took the longest. Another very nice statistic is the GC. You can see exactly what garbage collector events happened, and they were at all 3 events. 2 of them happened at generation 0 in the GC heap, and 1 and Gen 1. The pauses were around 16 milliseconds. That's not very good. And this is why it was, and how, and it tells you how it was triggered. In this case, it tried to allocate a small object, and it said, oh, hey, my heap has gone bigger, and I need to reduce that. So it did a garbage collection. So it can also show you exactly what you allocated. In this case, system string. So AngryBots really like strings. 37% of all the allocated managed memory in C#, and the Unity script is in strings. Yeah, no wonder there's performance problems. Right, and the last thing I'd like to show you, you currently can't do this yet, but you will be in Unity 5. We'll be adding our own event tracing for Windows provider that will tell you, that will show you events at each managed native transition. That is, you'll be able to see exact which native call is taking a long time, and you'll be able to identify what is expensive and what is not. For example, let's scroll down a little bit. Screen.width, that's actually a property, so it calls into native code, and that took 10 nanoseconds to complete. You shouldn't probably call that every frame because it's not 10, it's 3 nanoseconds, yeah. I was mistaken, sorry. But still, you should cache that and not call that every frame. That's my demo. So what have we learned today? First of all, you should always find the graphical limits on your target devices. You should always test on the slowest device first, because that's what's going to limit you in the end. Also, if you have performance problem, use a profiler, use tools that are made for figuring out these problems. Don't guess, because chances are you will not be able to do that very precisely. Remember, 2D games generally can afford more stuff than 3D games, so if you want to make something really pretty, it doesn't necessarily have to be a 3D game. One important point I want to make is reducing resolution might seem like a dodgy tactic, but it's on high resolution devices that are like full HD on 5-inch screen. It's a very viable solution. Chances are, if you reduce the rendering resolution by half, nobody will notice because the pixels are small, but it will allow you to draw twice as much stuff on the screen. For transparent sprites, remember to use the tight meshes. Of course, that's only available for pro users. But I guess that's... Yeah, and avoid transparency as a plague. Because if you have like 10 transparent objects in the scene, it doesn't seem like much, but it will just obliterate your performance on slower GPUs. Any questions?
Yes, please.
Is there a similar allocation tool for Android or iOS that will show what is allocated in the mono heap or the .NET heap?
So the question is about allocations on iOS or Android. Like Android is an evil thing right now because I'm iOS guy. He's Windows and like Android. But on iOS, have you tried the instruments? It has quite significant, and it's very similar to what Tautvydas showed. And
you know how he showed what C# objects, he showed the strings that were actually allocated.
Oh.
I'm looking for that information.
That might be really hard. Apple doesn't like giving out data.
It should be the same if you just run it on Windows Profiler.
Yeah.
Yeah, you'd need to be able to actually connect the game running on device to some profiler that understands .NET objects.
So we had the question in the back.
You mentioned changing the resolution or the render size.
Yeah.
Is possible on the mobile hardware?
It actually, you don't change the window resolution, but you can reduce the resolution at which Unity renders. I can't remember the exact API, but I think it's something with this in the screen class. You can set the resolution at which Unity renders, and it just upscales it.
Yes, please.
What about the overhead for the profiler? I've seen in the past that sometimes when I use the Unity profiler, you'll say like overhead as a number 1 or 2 item.
Yeah, overhead is pretty much whatever Unity cannot see. It's either something happening on the device, for example, rendering some native UI controls, but probably it's not that. But it's something that Unity cannot see. The only way to find out what exactly it is to use some other tool to profile it.
Which has more access to data, yeah. Like Xcode itself, or in this case, even Tracer.
Yeah.
Yes?
So did you also find out why Angry Birds needs that many strings?
Oh.
Yeah, it uses strings to identify game objects. It could use some optimization work, and I guess improving its performance would be a noble goal. Probably nobody wants to do that.
Yes?
Are there any tips for profiling your game with Unity free, aside from creating one email?
Unity free. So, as we told, internal profiler, have you tried that?
It works on free, and all the native profilers for platforms work on free as well. The one I demoed works. You don't need anything else than Windows SDK, which is free from Microsoft. You can use that if you're on Windows.
And for iOS, Xcode stuff.
Also, it might be worth, even if you're not publishing on platforms if you don't publish on Windows but you want to use the tools, chances are that the same bottleneck will exist on your game. So just building for that and testing, it doesn't have to really work well, but you'll be able to just use different tools, and maybe that will tell you exactly what's wrong.
Yes.
Do you have any tips on working with render textures? Like I know, like when you showed your sample profiling, like if it's fill rate bound and stuff like that, is there a way to work? Or have
It's. Do we have any tips for render textures? How to use them?
Not how to use them, how to...
Yeah, efficiently, of course. It's always about efficiency.
Right. I think that it isn't really different than profiling the GPU usage. I mean, you can use the Unity GPU profiler. It will show you exactly which render texture is taking a long time. Other than that, it really shouldn't matter whether you're rendering to the back buffer or the render texture. It's the same. Yes.
You mentioned being bound by CPU and GPU, but have you ever been bound by bandwidth, and can the Unity profiler help you figure that out?
You mean memory bandwidth on the GPU?
Yes.
So what was your question? Sorry.
Can the Unity profiler help you figure that out if you're getting a low FPS and you're not bound by CPU and GPU?
Actually, I'd say that being bound by GPU memory is kind of GPU bound. The Unity GPU profiler will tell you rendering which objects is expensive, and then when you have that info, you'll be able, by investigating more there, you'll be able to find out what exactly is causing the issue, whether it's memory or by increasing, for example, texture sizes, or it's fill rate by increasing rendering resolution or decreasing it. If you, for example, if you suspect that something is memory bound, like rendering a texture on a plane, for example, so increase the texture resolution size and see if the performance gets any worse. If it gets considerably worse, it means you're memory bound.
So if you need any examples how to use the tools we showed, just grab us on Hands-on Lab and we'll show you. Maybe give some.
Lab is over.
Okay, just find us.
Yeah.
So thanks, guys.